Hello all and welcome to this next video in the MPLS series. In the last video we saw about the theory of MPLS, why MPLS is needed, how labels are distributed, what are labels, what is LDP and how LDP works, what is penultimate hop popping, etc. So today we would be looking into the practical of MPLS in JNS 3, and we would be also looking into the Wireshark of how these packets are being transmitted from one router to the other router in an MPLS network. So before we move on in the video, I just want to set up the scenario here for you. So you see that we have four routers here, and all these routers are connected through OSPF. So they have an end-to-end reachability. I have 1.1.1.1 as the loopback for R1. Similarly, 2.2.2.2 is the loopback for R2. For R3 and R4, 3.3.3.3 and 4.4.4.4 respectively are their loopback addresses. So the network between R1 and R2 is 12/8. The network between R2 and R3 is 23/8, and the network between R3 and R4 is 34/8. So let's get on with the practical here. So as I was saying that these routers have an end-to-end reachability. So to create an end-to-end reachability, we will configure OSPF on each of these routers so that R1 can reach R4 through OSPF. So let's get on with that. Configuration terminal, and please feel free to skip this part of the video if you are aware of how to configure OSPF, but this is just a simple OSPF configuration, nothing much. But whoever wants to go through the flow of the video, please continue. Others can just skip to the part where MPLS will start. Thank you. So configuration terminal, uh, router OSPF1, and I'm just going to enable OSPF on all the interfaces. So I would just give network 0.0.0.0, 0.0.0.0 also as the wildcard mask, and area sorry area 0, right? And I would do the same configuration on R2, configuration terminal, router OSPF1, network 0.0.0.0, wildcard mask is also 0.0.0.0, and area is 0. And on R3, configuration terminal, router OSPF1, network 0.0.0.0, 0.0.0.0, area 0. And on R4, configuration terminal, router OSPF1, network 0.0.0.0, 0.0.0.0, area 0. And so after enabling OSPF on all the routers, you can see that the OSPF neighborship with their neighboring routers is up on R1, R2, R3, and on R4. So the next step is that we'll enable MPLS on each of these routers. So to enable MPLS, I'm going on an easier method where I will just enable MPLS based on the interface. So let's go to the interface fast Ethernet 0/0 on R1, and I will say MPLS IP, right? And let me also enable Wireshark or packet capture on this interface. Start capture. Meanwhile, as this is capturing, let's go back. Now, what I will do is I will also enable MPLS IP on the interface fast ethernet 0/0 of R2, not on fast ethernet 0/1, which is facing R3. So configuration terminal, interface fast ethernet 0/0, MPLS IP, and end. So the moment I do that, if you see here, it says the LDP neighborship has changed. The LDP neighbor is 1111, which is the LDP identifier of R1, and that is up. So let's see that on the Wireshark. So if you see here, the first packet that you see is the OSPF message, OSPF packet that once we enable the OSPF, the routers are sending it to each other. But we are not interested in that. We're interested in the MPLS message or the LDP message. So let's check those. Here, if you see that your source is 12.0.0.1, that's the interface IP of router. This is your multicast address of LDP, that is 224.0.0.2. Okay, so let's open these messages here, and in this message we will see an Ethernet message, sorry, Ethernet packet. Then we would see an Internet Protocol IPv4 packet. Then we have a UDP packet. Okay, if you remember in our previous video, I mentioned that when a MPLS hello message is sent, it's sent on a UDP port, and that UDP port is 646. Okay, and it is sent, and the message that is sent is an LDP packet, right? And if you can see here, the LDP packet that is mentioned is, sorry, the LDP identifier that is mentioned is 1.1.1.1. Okay, and what kind of LDP message is this? It is a hello message. And if you see here, the transport address is also 1.1.1.1. So basically your LDP identifier and your transport address by default are the same. So what is this transport address, right? IPv4 transport address. If you remember from my last video, once your UDP session is set, with the UDP session, the MPLS speaking routers identify each other. Once that is identified, they start a TCP session with each other to exchange their labels so that they can form their label bindings, right? So the transport address or your TCP session is basically, your TCP session is created over this transport address 1.1.1.1. So here in our example, R1 is basically telling R2 that, buddy, if you want to create a TCP session with me, so you need to create a TCP session over 1.1.1.1. Okay, so let's continue that, and we will see that there is a TCP session created with these transport address. So if you see here, all these messages are LDP messages. Hello message is being sent by R1, okay, on the multicast address 224.0.0.2. Okay, now let's scroll down. The moment I enabled MPLS on R2, R2 also started sending hello messages, right, through its exit interface 12.0.0.2 on the multicast address 224.0.0.2, right? So now R1 and R2 have identified each other through the LDP messages. So your UDP session is set with the UDP hello messages on port number 646. They identified each other as MPLS neighbors, right? And then if you see here, there is a TCP session created with SYN, SYNAC, and ACK. That is your TCP three-way handshake. Okay. Then once the TCP session is completed, as I mentioned, an LDP binding will start, or LDP mapping. So basically R1 and R2 are exchanging their labels with each other. So if you see here in the next couple of steps, you will see LDP messages being, labels being exchanged with each other. So if you see here, address message, label mapping, label mapping, right? So you will see that R1 and R2 are exchanging their labels of the fib with each other. Once the label binding is completed, you have the TCP session termination. I hope this was clear. We will get inside the label binding in Wireshark later. But for now, let us see that what are the label bindings that R1 and R2 have done for the fib destination networks in their LFib. So let's do a command show MPLS LDP bindings. So if you see here, R1 has these entries in its fib, that is 1.1.1.1, 2.2.2.2, 3, 4. It has also entries for 12 network, 23 network, and 34 network. So for all these networks, it has assigned labels to it. So there are two types of labels, as we saw in our previous video. There are two types of labels. One is a local label and the other is a remote label. So for 1.1.1.1, which is its own uh, uh, loopback address and it's directly connected to it, that local label binding is implicit null. Okay, and if you remember, the implicit null value is 3. Next, for that same label, it has received a remote label from the LDP identifier of 2.2.2.2, which is R2, and R2 has assigned a label 16 to it. So 16 is the remote label. 16 is the remote label for 1.1.1.1, and the implicit null, that is value 3, for that is the local label that R1 has assigned. Similarly, if we see for 2.2.2.2, the local label that R1 has assigned is 16, and R2 has assigned implicit null to it, which is value 3, because 2.2.2.2 is the loopback address on R2 and is directly connected to it. For 3.3.3.3, the local label on R1 is 17, and R2 has given a remote label of 17 as well. In our previous video, we saw the labels being different. I used different labels in order to avoid confusion for theory's sake, but in real time, the labels for the destination network on both the routers may be same, may not be same. So just do not get confused. The local binding for this network on R1 is 17, and R2 has sent the same label for as 17 to it. These two labels are different. This is a local label, this is a local label, and this is a remote label. The routers are very well capable of differentiating these two labels. Though the label number is same, but for the router, these two labels are different. So if you can see, there are local labels assigned by R1 and remote labels assigned by R2 that have been exchanged between these two routers. Let us confirm these values in the Wireshark. So if you remember, I said the value of implicit null is basically 3. How do we know that? We'll check that shortly on Wireshark. But anyhow, if you remember, just keep the label bindings in your mind. R2, whose label binding, sorry, whose LDP ID is 2.2.2.2, is sending the labels 16 and implicit null, 17, 18, and two more implicit nulls, and 19 label to R1. Let's cross verify that. So for 1111, R1 has received a label of 16 from R2. Let's check that on Wireshark. So here, if you see, the source is 2222, the destination is 1111. So this is being sent by R2 to R1. Okay, and here these are the messages. So if you see here, it says label mapping message. Okay, now on the label mapping message, for prefix 1 dot, okay, where did 1 dot, okay, yes, for prefix 1.1.1.1, R2 sent a label of 16. Let's check that on on the table, our LDP binding table. For 1.1.1.1, R2 sent a label 16, correct? Now let's go for 2222. The prefix is 2222, which is the LDP identifier as well as the loopback address of R2. For that, the generic label is basically 3. And in our LDP binding on R1, you will see an implicit null value, right? So this proves that our implicit null value, that label, is basically 3, right? And R2 has sent 3 label for 2222. For 3333, R2 has sent a label 17. Let's check that on Wireshark. 17 label, you can see here, label is 17, and if we open the prefix, it is 3333. For 3333, R2 has sent a label 17. So we can check similar mapping on Wireshark as well. So this confirms how label mapping is being done in after a TCP session is set. Once you enable MPLS on R1 and R2, a UDP session is created, or UDP a UDP session is created, and with the UDP session, LDP hello message is sent. Once the LDP hello messages are received by both the routers, a TCP session is created with the three-way handshake SYN, SYNAC, and ACK. Once the TCP handshake is over, a label mapping happens that we saw here, and in each of these label mappings, they exchange their labels for each of the prefix that they have in their fib. I hope till here everything is clear for you guys. Now let us enable MPLS on all the other routers. So we enabled MPLS on R1 and R2. Let's enable MPLS on R3 and R4 as well. So configuration terminal, and I will enable MPLS on both the interfaces. So on R2, I did not enable MPLS on fast Ethernet 0/1. Let me enable there. Configuration terminal, interface, fast Ethernet 0/1, MPLS IP. And on R3, interface, fast Ethernet 0/1, MPLS IP, interface, fast Ethernet 0/0, MPLS IP, and on R4, configuration terminal, interface, fast Ethernet 0/0, MPLS IP. And so the moment I enable MPLS, you can see that there are syslogs created which say that the LDP neighborship with 3333 is up. This is on R4. Similar message you can find on R3. It says the LDP neighborship with 4 is up, LDP neighborship with 2 is up. So now what we are going to do is that we will ping from R1 to R4, that is their loop back, that is from 1111 we'll ping to 4444, and then we'll see what is happening, how the labels are being exchanged. But before we do a ping, let me note down the local label and remote label of each of these routers and bring it on a visual manner. To understand these visually, what I have done is I have mentioned the fib of each of these routers, right? And what I will do is I will note down the local label and remote label of all these routers on the whiteboard. So it's easier for you to understand. Let's look at R1's LFib, okay, or label bindings. For 1111, it has a label of implicit null. And from Wireshark, we understood that the implicit null value is 3. And the remote label for the same is 16 that it received from R2. So let's just concentrate on the local bindings for now. On R1, the local binding for 1111 is 3. So on R1, the local binding for 1111 is 3. For 2.2.2.2, the local binding is 16. For 3.3.3.3, the local binding is 17. For 4444, the local binding is 18. For 12.0.0.0 network, the local binding is implicit null. That means the value is 3. For 23 network, the local binding is 19. And for 34 network, the local binding is 20. Now let's get on to R2. On R2, let's do a show MPLS local binding. So we will see for 1111, the local binding is 16. Local binding for 1111 is 16. For 2.2.2, the local binding is implicit null because it's directly connected. So the value is 3. For 333, the local binding is 17. For 4444, the local binding is 18. For 12 dot network, the value is implicit null because it's directly connected. So that value is again a 3. For 23 network, that value is again 12. Sorry, implicit null, that is 3 because it's directly connected. And for 34 network, the local binding is 19. All right. So after a TCP session is established with R1 and R2, they will exchange these label bindings with each other. Okay. So on R1, the remote label for 1111 would be 16 here. For 2222, it would have received an implicit null value, and that is 3. For 3333, it would have received a value 17 from R2. For 4444, it would have received a value 18. For 12.0, that value is 3 from R2. For 23 is also 3 from R2. And for 34, that value is 19 here. Let's verify that. So on R1, the remote label for 1111 is 16. For 2222 is implicit null value, that is 3 here. Then we'll see 17 and 18, 2 implicit null and 19. So let's check that. 17, 18, 2 implicit nulls and a 19 value, right? So our label bindings on R1 is complete in this diagram. Here is the final look of the LFib on all the routers. So just to avoid the confusion, the local labels on all the routers have different colors, and the remote labels on all the routers according to the labels that they have received from their neighboring routers is also different. So what we are trying to understand here is that if I do a ping from 1111 to 4444, how will the label switching happen here? We'll look this on the GNS3, and we will understand this visually on this whiteboard, as well as we will check this same theory on the Wireshark as well. On R1, let me do a ping 4.4.4.4 from the source 1.1.1.1. Okay, when I did a ping, it is sent. So when I did a ping from 1111 to 4444, what R1 basically does is, first it checks its MPLS LDP binding, right, which we have been checking now. So for 4444, okay, it sees that the label binding that it has assigned is 18. Okay, then the next thing that it does is that it has to check the routing table, show IP route. When it checks in its routing table, it finds that 4.4.4.4 is reachable via the next hop, that is 12.0.0.2. And what is the LDP identifier that is associated to 12.0.0.2? You will understand this concept when we reach on R2. Okay, so it tries to identify the LDP identifier for 12.0.0.2 that it knows is through show MPLS LDP neighbors. When it does that, it sees that for 12.0.0.2, the LDP identifier is 2.2.2.2. Okay, now then it checks show MPLS forwarding table. When it does that, now it has the whole information. In this forwarding table, it knows that for 4.4.4.4 network, right, the next hop is 12.0.0.2. So if I want to reach 12.0.0.2, I have to assign a label 18 to it. And as per our LFIB, that 18 value which we received from R2 was 18, right? So as you remember from our last video, a remote label is used to send the traffic, whereas the local label is used to identify the incoming traffic. So here 18 is the outgoing label which R1 will assign to the traffic and forward it. Now you may ask this question, why did we go through all these four tables, right? The forwarding table that R1 has created is created based on the above three table. The first thing that R1 does is that for the destination IP address that we have typed, the 4.4.4.4, what is the MPLS binding that it has created in its LFIB, MPLS LDP binding. So it knows that 4.4.4.4, for 4.4.4.4, the label that it has assigned is 18, and I have received a label of 18 from someone that is 2.2.2.2. But where does this 2.2.2.2 reside, right? So it has to check that. So 4.4.4.4 is the destination address. So let me check in my IP routing table, where does this, how, not where, how to go to this 4.4.4.2. Okay, so to reach 4.4.4.4, the next hop is 12.0.0.2. Is 12.0.0.2 the identity, is 12.0.0.2's identifier 2.2.2.2? Let me check that. So it checks it with show MPLS LDP neighbor. It sees that for 12.0.0.2, the LDP identifier is 2.2.2.2, right? So next in this show forwarding MPLS forwarding table, It knows that now it has all the information. It knows the destination network that it has to go. It knows that the next hop address is 12.0.0.2. The 12.0.0.2's identifier is 2.2.2.2. So for that, I have to assign a remote label or an outgoing label of 18 and forward it to my next hop, that is 12.0.0.2. And where does this 12.0.0.2 reside? Okay, if I have to reach out to him, I have to send my packet out of fast Ethernet 0/0 interface. That is why your IP routing table is also important for the router to understand the outgoing interface. So here in our example, what it does, it assigns label 18 to the traffic and forwards it to R2. Okay, it forwards it to R2. Let's verify that on the Wireshark. So on Wireshark, here we did a ping from 1.1.1.1 to 4.4.4.4. If you remember, in our first session, I had mentioned that MPLS is a layer 2.5 layer. We also call MPLS as a layer 2.5 protocol, right? So if you see here, you have the Ethernet packet and then you have the IPv4 packet. And in between these two frames or packets, you have the MPLS, right? If you see here in this, you will see MPLS protocol and the label that it has assigned is 18, which is the remote label that it assigned to send this traffic. And this remote label is also the local label of R2. Okay. Now coming back to the diagram, what will R2 do? What R2 basically does is it checks that it has received a label of 18. Then it checks in its LFIB to what destination network that it is assigned for, that is 4.4.4.4. Now the next thing that it checks is that for 4.4.4.4, how will it reach that destination network. So in its routing table, it sees that for 4.4.4.4, the exit interface is 23.0.0.3. Okay, now this 23.0.0.3, what is the LDP identifier for it? So it will check that what is the LDP identifier of 23.0.0.3, that is 3.3.3.3. Okay, then in its forwarding table, show MPLS forwarding table, it has all the information. It now knows that the 4.4.4.4 is basically the destination network. Okay, the next hop for that is 23.0.0.3, and 23.0.0.3 is basically identified with 3.3.3.3. Okay, now that 3.3.3.3, I have to assign an outgoing label of 19 to it. Okay, so why routing table is basically important? Okay, it received a label of 18 from R1, right? So now it checks that 18 in its LFIB is assigned for 4.4.4.4. Now, to avoid this confusion, 4.4.4.4, it has two remote labels. One is 18 and the other is 19. So should it use the 19 label or should it use the 18 label to forward the traffic? If it uses the 18 label, it is basically going to send it back to R1, which it does not want. It basically has to send it to R3. How is it going to erase that confusion? For that, it has to check the routing table. So let me tell you this step again. What it does is it checks the show MPLS LDP bindings, where it sees that, okay, it sees that it has received a label for 18, right? That 18 label in its LFIB, in its LFIB, that 18 label is assigned for 4.4.4.4. Okay, so in for 4.4.4.4, what would be the next hop so that it can change it? Okay, for 4.4.4.4, it has two remote labels. One is 18, the other is 3. But still, as human, we know that 18 label that came from 1111 is its previous hop. But how will the router avoid this confusion? So it has to check the IP route, show IP route. Here it now knows that for 4444 the next hop is 23.0.0.3. So 23.0.0.3's identifier, what is it? Now for 23.0.0.3, that identifier is 3333. So if I have to go back, so if I have to forward 23.0.0.3, I have to use the remote label that I received from 3333. So I have to use a label 19 to it. This can be again verified in the show MPLS forwarding table. Okay, so the MPLS forwarding table is basically populated using your MPLS binding, your show IP routing table, and your LDP neighbor table. So now it knows the next hop is 23.0.0.3. Okay, and for that the identifier is 3333, and my destination network is 4444. So I have to use a remote label of 19 and forward the traffic. So now in this case, what it is going to do is it is going to swap the label 18 with 19 and forward it to R3. Okay, let's verify that on the Wireshark. So here, if you see, we have a ping from 1111 and it goes to 4444, right? And in our case here, this label is 19, which is the outgoing label that R2 has assigned for this traffic. Now this traffic has reached R3. Okay, it has reached R3. So it sees that I have received a label of 19. Okay, now in my local table, my LDP binding, what this 19 corresponds to? This 19 corresponds to 4444. Now for 4444, I have two remote label bindings. One is 18, the other is 3. What am I going to do? So again, it does the same check. R3 basically first checks the show MPLS LDP bindings, where it sees that, okay, it has received a remote label 18. In its LFIP, that 18 corresponds to 4444. Okay, that label corresponds to 4444. Now how will it reach 4444? So in its show IP route, it knows that for 4444 it has to go via 34.0.0.4. So for 34.0.0.4, what is the LDP identifier? It checks show MPLS LDP neighbors. So for 34.0.0.4, the LDP identifier is 4.4.4.4. Now in its show MPLS forwarding table, it has all the information. The destination network is 4444, right? The next hop address is 34.0.0.4, for which the identifier is 4444, right? So what is it going to do? I basically have to pop the label. There is no label swapping, but then I have to pop the label. When it needs to pop the label here, right? If you see, 19 is going to be exchanged with label 3. Basically, it's not going to be exchanged. 3 means it's an implicit null. So R4 basically is telling R3 that if you have to send a traffic to 4444, right, there is no need for you to tag it with a label, but instead you pop the label and forward it to me. Okay, so here basically what R3 is going to do, it's going to erase the label and forward the traffic in a normal fashion. That is your normal IP routing. So let's check that on Wireshark. So on R3's interface, if you see 1111 is the source, 4444 is the destination, and in this you will notice that there is no MPLS layer in between these two, Ethernet and in IP layer. Okay, it's just a normal traffic. What R4 is going to do, R4, as per our diagram, R4 receives it. R4 receives a traffic of, R4 basically does not receive a label traffic, it just receives a normal traffic. So R4 here in our example is only going to see a normal traffic with a destination IP of 4444. So what R4 is going to do, it is just going to check its routing table, show IP route. In that it will see 4444 is the directly connected loopback address, and it's going to forward the traffic to the loopback, and the loopback is then going to send a reply back for the ICMP request. So this is how your MPLS labels are basically pushed on R1, swapped on R2, and popped on R3. I hope with this practical the MPLS working was clear. Please do like, share and subscribe this video, and do let others know about this. Thank you and have a great day. It has received a label 19 to it, right? Now LFIB, in its LFIB, okay, it has label 19 received from two different routers. One is from R2 and the other is from R4. Which neighbor should it forward to? Okay, so R3 also does the same check. In its LFIB, right? In its LFIB, it sees that the label 19 that it assigned was for 4444. Okay, now it has to forward the traffic. Okay, now for 4444, it has two remote labels. Okay, one is label 18, the other is with an implicit null. Okay, to which neighbor should it be forwarding to? Should it forward to a neighbor 2222 assigning label 18, or should it forward to neighbor 4444 with an implicit null value? It has to remove that confusion, right? So it goes to the show IP route. Okay, and in that it finds that 4444 has to go out via 34.0.0.4. What is the LDP identifier for 34.0.0.4? That it finds out through MPLS LDP neighbor table, right? For 34.0.0.4, the LDP identifier is 4444. Now it goes and checks in its forwarding table, show MPLS forwarding table. It now knows that for a destination 4444 with an outgoing interface or the next hop as 34.0.0.4, there is no label to be assigned, but it needs to pop the label. Okay, if you remember our penultimate hop popping, right, for 4444, okay, the next hop being 34.0.0.4 and the LDP identifier being 4.4.4.4, it had received a label of 3. Basically, here it is going to pop the label that it received. It received a label 19, right? It received a label 19 from R2, and it checks all the table and finds out that it needs to forward to R4. But R4 has said that I need an implicit null label for it, that is 3. So it is not going to swap the labels, but it is going to pop the label on R3. It is going to pop the label R3 and it is going to forward the traffic without labels, meaning that this is going to be a normal IP forwarding. So On your Wireshark, let's check. Now, between R2 and R3, if you see, there is no MPLS label between these two layers. So here the traffic is being forwarded normally. Okay, and on R4, R4, all R4 does is it sees the destination IP, that is 4444, right? And on 4444, as per our routing table here, because there is no label assigned to it, this is just a normal IP traffic that R4 received. So it's not going to check any of the MPLS table, it's just going to check its routing table. So in that routing table, it sees that 4444 is a directly connected loopback address. Okay, and it is going to respond back to R1 in a similar fashion. I hope the forwarding of traffic using MPLS label was clear. And if you like this video, please subscribe and share with your friends. Thank you and have a great day.